And we're back. Welcome back and happy Tuesday. Today, we will switch gears and talk about something related to regularization, namely validation. But before we begin, some administrative bits. The reading: Overfitting, Section 4.1, for regularization, Section 4.2, and validation, Section 4.3. Homework number 3 is due the 6th of April, a week from today, at the usual 1 second before midnight, 11:59 and 59 seconds p.m. All right. When we last left off, we came up with a formulation for regularized regression, and this involved something that looks like the pseudo-inverse, but we have this extra term, lambda I. And if that lambda is big, this quantity, our weights, are small. If lambda is small, our weights are big, and that is the opposite of what happens to our weight budget C. And this is in contrast to the unrestricted regression problem. It's the pseudo-inverse, the W-Lin solution. And we also gave a depiction of what happens when you set your regularization parameter to be increasingly big under stochastic noise and deterministic noise. They both behave the same for our expected out-of-sample error. Alrighty, so let's take a look at regularization. So with validation, it's a little bit different. For regularization, we had out-of-sample error is in-sample error augmented with an overfitting penalty. And regularization estimates what this quantity is. You have your regularization parameter, and it essentially turns up the amount of regularization applied to your augmented in-sample error expression. Now, validation, in contrast, it estimates directly, cut to the chase, estimates directly our out-of-sample error and makes model choices based on that estimate of out-of-sample error. And so let's take a look at an analysis of our out-of-sample error estimate. Now, of course, error on a single out-of-sample point, x, y, label, is our pointwise error. That's some difference between the ground truth target function on that out-of-sample point and our hypothesis h of x. Now, for the regression problem, we have the squared error loss function, and that squared error loss function concerned ourselves with the magnitude of the difference and not whether or not it was positive or negative. And for classification problems, we had a binary error, which asked the question of, is the output of h of x the same as the +1 -1 label from the unknown target function? And so if we take expectation of the error on this single out-of-sample point, we get out-of-sample error E out for that hypothesis. Now, if we take the variance of this expression of our pointwise error on that single out-of-sample point, we're going to get something we called sigma squared. Now, let's imagine then we have a set of out-of-sample points. We call this our validation set. So we have big K of them, where K is going to be our validation set size. So we're given a set of label instance pairs, x1, y1, x2, y2, up to and including x big K, y big K. And so if we were to compute the validation error on this validation set, we would take the average pointwise error summing. So here we have 1 upon K. Little k goes from 1 to big K. Our pointwise error E between h of x and y for each of those points in our validation set. Now, of course, if we take the expected validation error, well, the expectation of a sum is the sum of the expectation. So we can bring this E of x inside of the summation, and we know that the expectation of our pointwise error, that's just E out for our hypothesis set. And if we take this is a constant, we're adding it to itself big K many times. We're dividing by K, and that's just E out for our hypothesis set. And so the expectation for this validation set is exactly E out. Now the variance, on the other hand, if we take the variance of this validation error, variance of eval, well, the variance of a scalar is that scalar squared. We can pull that out. And then the variance of a sum is the sum of the variance by linearity of variance. So we have that 1 upon k squared, the sum for little k goes from 1 to big K, variance of that pointwise error, E of h of x between y of x from the unknown target function. And so now if we do this, well, the variance of our pointwise error we said was sigma squared. So that's going to be a sigma squared, which is a constant. So we're adding sigma squared to itself, big K many times, that's K times sigma squared. Well, we have a copy of K in the numerator, a copy of K in the denominator, so we're left with sigma squared upon K. And so this is a stochastic quantity. We have this validation error based on what we choose for a particular validation set. It's going to change in its value. It's certainly its expectations out of sample error. But for a given validation set, you're going to get something that might be higher, something that might be lower. And so if we express what eval is, that's just E out, which is what we're looking for, plus or minus standard deviation, which is the square root of the variance. And so we leave out sigma squared because it's a constant, and the only dependent value that makes the variance bigger or smaller is this K term, the size of the validation set. And so we take the square root of this variance, and we write it in big O notation, 1 over radical K, because we're taking the square root of this variance, square root of K in the denominator. Now, if we have a large validation set, that means that this quantity, this variance, is going to be very, very small, and eval is going to be very close to E out, even though it's changing a little bit. If K is very small, on the other hand, then they're going to be very far off for a particular choice of validation set, because that variance is going to be large if K is small. And so when we look at this validation set, the question then is, how do you select K, the size of the validation set? You would want the variance of eval to be small, and therefore pick K to be large. But it's not so easy to do. There's a trade-off here between the quality of the estimate of out-of-sample error that the validation set affords you and the size of that validation set. And so here we have our data set, and carved out of that data set is going to be K many points, and that's going to be our validation set. We call that DVAL. Now, of course, if you have N many data points from your data set, N minus K are then going to be used for training. We call this detrain. And so there's this competing tension here. While we want K to be large, because that means the validation error is going to have a low variance, if K is too large, that robs your model from its training set. The training set is getting robbed, and it's going to be much smaller, and you're going to have poor performance out of sample in your final best hypothesis if your training set is small. And so what happens is, okay, well, if you have small K, you're going to get a bad estimate of out of sample error and make poor model choices if your validation is used for model selection. But if you have large K, you can have good estimates, but you're going to have a good estimate of a really bad final best hypothesis, poorly performing out of sample. And that's almost like saying, I'm absolutely sure that your performance is going to be horrible if you have this large K. And so here, along the lower right, we have a learning curve of sorts, and the number of data points for training increases as we go to the right, and therefore K is going to decrease as you go to the right, but the number of data points that you have, N minus K, for detrain, is going to get smaller as you go to the left, and that means K is going to get bigger as you go to the left. So what ends up happening If K is bigger, we're closer to origin. Your out-of-sample error is going to be really, really bad because you have a small number of data set points on which to train your model. Now, of course, your estimate of out-of-sample error is going to be precise, but it's going to be precise about something that's really, really bad. As you increase the number of data points to train on, well, E out is going to come down, E in is going to increase, and E in increases because you have more data. But you'll notice here the gap between E in and E out gets closer and closer, and that's sort of things inequality working in action because you have more training data. And so there's this natural tension between K, the validation set size, and the training set. How do you strike this balance? Well, one of the things you can do is you can use your validation set to make model choices, and then once you're done making those model choices, influencing the learning approach, you then put it back, join it back with the training set, making the original data set that you then train your model that you've selected on the full data set, giving you the maximum training data you can have to get your final best hypothesis. Now, of course, if you're going to train on n minus k, that training set derived from taking your data set and removing your validation, that's going to give you detrain, and detrain, when you train on your hypothesis set, you're going to end up with what the book calls G minus. It's a limited version of your final best hypothesis because it didn't have all the data that was available. Now, of course, depending on the size of K, there's going to be a gap. There's going to be a difference between G, the final best hypothesis on the full data set, and G minus, the final best hypothesis on detrain, which is the full data set with that validation carved out of it. And so when you think about eval, your validation error, is evaluated by taking DVAL and running it through that G minus. And when you do that, what you're reporting is something different from your final best hypothesis G, because it's a little bit off. It's not your best final best hypothesis. And so the difference between G and G minus is going to be very large if K is big. Why? Because if K is big, detrain is going to be much, much less than the full data set D. And if it's much, much less, then you're going to have a suboptimal final best hypothesis, G minus. And so here we have our original data set. We carve out our validation set using K many of those in-sample points. We then are left with detrain. From detrain, we produce our G minus. And then we take our DVAL validation set, run it through our limited final best hypothesis G minus, and get our validation error on that limited final best hypothesis. Now, once we are done and we make our model choice, we then take K and recombine it with detrain to give you the full data set using that same model that we selected because of eval and this limited hypothesis G minus, and then we get an even better version of G minus. We get the full final best hypothesis G. And so if K is small, it's going to have a high variance. But if K is big, this difference between G minus and G is going to be really, really large. And so a rule of thumb is to use a validation set size K that is 1/5 of the total in-sample set of data. K equals n upon 5. So let's take a look at using DVAL to make learning choices. This could be the selection of a regularization parameter, or it could be something like early stopping. Now, of course, when DVAL is used to influence or make model choices or learning choices, it no longer acts like a test set. Now, of course, what it's acting like is an estimate of out-of-sample error, and we're going to use this estimate of out-of-sample error to evaluate the impact that a model choice would have on out-of-sample error. And that's what we use DVAL for, and it's no longer a test set. And so essentially what it's doing is giving you an early look at how a model choice might affect out-of-sample performance and then taking action based on it. And so in the case of this learning curve, training for a neural network, we have a number of epochs along the horizontal axis, and we have error along the vertical axis. The green curve is in-sample error, and the red curve is out-of-sample error. And so as we train over epochs, going through the forward pass and the backwards pass, the forward pass and the backwards pass for a neural network each time on each round, updating our weight vectors, as it tries to mimic the unknown target function, the in-sample error of this neural network training regime starts to decrease. And we also see that E-out starts to decrease. Now, of course, if we're using DVAL to estimate out-of-sample error, at some point we're going to see, oh, that estimate is going to start to increase. And that's the point when overfitting happens, so we can stop it at that point when we see that estimate from eval, our estimate of E-out, start to increase when E-in continues to decrease. We can now do something about it, and that stops the training. Okay, and so this introduces an optimistic bias. And so a test set itself is unbiased. A test set is what you do when you set aside data that you do not use to influence your model choices. A validation set, on the other hand, introduces a so-called optimistic bias. It gives you the false sense that things are really better than they are. And the reason for this stems from the fact that a validation set involves choosing the best from a number of alternatives. So let's imagine an example where you have two hypotheses, H1 and H2, and their out-of-sample error for each one, let's imagine it was 0.5, and the estimates for error for each one of these hypotheses, E1 for H1, E2 for H2, they're going to be uniform in the closed interval between 0 and 1 on the real number line. And so these are error estimates, and now based on this error estimate, which is akin to eval, we're going to select some hypothesis H from this set H1, H2 that is the minimum estimate. And so essentially, one of the things we're going to see is that even though their expected out-of-sample error is 0.5, we know that the pick between these two hypotheses based on these two estimates is going to be less than 0.5. And so the probability that one of them is 0.5 is a 75% probability. So what does that mean? So let's say we have H1, and let's say that could either be less than 0.5, H2 at the same time less than 0.5 error, H1 is less than 0.5, H2 is greater than 0.5, and then let's say H1 greater than 0.5, while H2 is less than 0.5, and then that last scenario is H1 is greater than 0.5 error. At the same time, H2 is greater than 0.5 error. So if we look at this event that we get for a minimum, and we consider the probability that one of these two, because we're selecting a minimum, one of them is less than 0.5, well, we have one alternative here. They're both less. Here's another one. H1 is less. Here's another alternative. H2 is less. This one does not. They're both greater than 0.5. So we have 3 out of 4 total choices. So that's a 75% probability that one of them is less than 0.5. So what does that mean? It's very likely that the expected error, E, that we arrive upon from the minimum between E1 and E2, that's going to be less than 0.5 because 75% of the time, one of them is going to be less than 0.5. And this is this optimistic bias because it's not quite as good as their expected out-of-sample error, it's going to be less than that. And that optimistic bias comes from the fact that you're making a choice from a bunch of alternatives looking for the minimum. Okay, so let's take a look at model selection. And so we have a bunch of models, and these models can be a number of different alternatives. One could be, for example, different degree polynomials. So we could have a set of degree 10 polynomials for one model, H1. We could have H2 is another, say, degree 20 polynomials, and so forth. So they could be completely different hypothesis set, degree 40, for example, or they could be the same function class or family of functions. They could all be degree 10 polynomials, but each model could be different based on, for example, the regularization parameter. So maybe this one is degree 10 with regularization parameter is 0.01. Then we have this next one, degree 10, with regularization parameter lambda equals 0.02, and so forth. And so each one of these differences are valid ways of having some number of big M many models. Now, of course, from this, we're going to use dtrain, which is the training set that results from carving out a validation set from your in-sample points, your data set. And so we're going to use dtrain to learn our limited final best hypothesis, GM minus, for each one of these models. And so we're going to have a GM1 minus. We're going to have a G2 minus. We're going to have a G3 minus up to a GM minus. And each one of these GM minuses is going to be the resulting final best hypothesis for each of these big M many models when we run using dtrain to learn. And so then once we get these GM minuses, we're going to evaluate each of them using DVAL. And this is going to result in eval, or validation error, for each one of these GMs. So we're going to have eval for this one, G1 minus. We're going to have eval for G2 minus, and so forth. And so here we have our schematic. You start out with your training set D, and you split that up into your training set of size N minus K, and your validation set of size K. Now, using dtrain, we run learning with each one of these hypothesis sets, and each one results in a different limited final best hypothesis. From H1, we get G1 minus. From H2, we get G2 minus. And for HM, we get G big M minus. Now, once we have these limited final best hypotheses, we're going to then evaluate DVAL for each of these limited final best hypotheses. And this is going to give us eval. Eval 1 from the first one, eval 2 from the second one, up to and including eval big M for the mth one. And so now that we have these evals, these validation errors, we're going to pick the best one, the one that's smallest, and that's going to be the model choice we're going to choose to go forward with the full training set. And so let's call EM the best validation error from these big M limited final best hypotheses. Now, if we call that M star, EM star, that means that we're going to have this mth hypothesis is going to be the one we're going to use with the full data set. So then we combine our validation set back with our dtrain to get the full set of in-sample points, and then we take that mth model and run the full data set through it, and we get GM star. And you'll notice that's not GM star minus, it's GM star because it's not limited. We've given it the full data set. And so we select the model associated with the smallest validation error, EM. Okay, and this is the approach that you use in using your validation set to make model choices. So you select the best model using hypothesis associated with the smallest validation error on this limited final best hypothesis, GM minus. And we select that model as a result of applying our validation set, DVAL. And so eval for each of our limited final best hypothesis is a biased estimate of out-of-sample error on GM minus. It's biased because we're choosing a maximum. And so we illustrated that before when we had H1 and H2. We talked about this optimistic bias. So if we look at the learning curve and the relationship between eval of GM minus and E out of GM minus, on the horizontal axis, we have our validation set size, and let's assume our data set size 30, and our validation set size increases going to the right on the horizontal axis, and our expected error, E out, is going to be along the vertical axis. So here, one of the things we see is that as the validation set size increases, the gap between E out and eval gets smaller and smaller and smaller. Now, the reason for that is because as the validation set size increases, it becomes a better and better estimate of out-of-sample error. And so here, the bigger that K gets, E in and E out get closer because eval becomes a more reliable estimate of out-of-sample error. But again, the problem is that as you increase the validation set size, E out, you'll notice, increases. And it increases because dtrain gets smaller as you move to the right. And if dtrain gets smaller, that means out-of-sample error performance gets worse because you're limiting the data set that your hypothesis set needs in order to have good or better out-of-sample error. Okay, and so with bigger K, the estimate of out-of-sample error gets more reliable, so they get closer. But the bad news is, with bigger K, your eval is a more reliable estimate, but your E out gets bigger. So let's consider what happens when we have all those models. When we trained those models, H1 through HM, on your D-train, we ended up with our suboptimal final best hypotheses, G1 minus, G2 minus, up to and including GM minus. Now, you can think of that set of suboptimal final best hypotheses as just a set of functions. And so as a set of functions, you could treat them like they're yet another hypothesis. This particular hypothesis, we'll call it HVAL, and it consists of big M many functions, so it has a size. So given that we take DVAL and we run that DVAL through our hypothesis set, evaluating each one of these hypotheses, G1 minus through GM minus, and we use it as the basis of selecting the best performer from these M many suboptimal functions, that looks a lot like training, and it kind of is. So you're using this DVAL to effectively train these finalists from these hypothesis sets, these final suboptimal best hypotheses. And so as such, it looks like training, and treating it like training certainly Herfting's inequality applies. And so we can think of it as E out of our GM star minus, that is the best of these GM minuses, that E out on that selection, that final best hypothesis from this hypothesis set, is what you get from using DVAL. That's going to be at most eval on that final best hypothesis from HVAL, plus a complexity term. And that complexity term is proportional to the size of the hypothesis set, HVAL, that's M. There are M many of these functions. And we have here K, the size of the validation set, which acts like the training data set size for this particular specialized hypothesis set. And so validation error acts like training error on this special hypothesis set, and therefore we can use Herfting's inequality to describe it. But for the infinite case, of course, like things like regularization parameters, we use a VC analysis. And so we can use this validation, as we said, for early stopping, but it's a little different from the regularization case. All right. So let's think about this idea of the consideration of when you use some data to make model choices. Now, of course, you have in-sample error, you have validation error, and you have test error. Now, when we think about this idea of contamination, whenever you use data to make a choice, you're overly optimistic about what your out-of-sample error estimate is going to be. Now, if we think of the training set, that's very contaminated. We're using it to determine which of the working hypotheses we're going to choose from among your hypothesis set. So again and again and again in this series of rounds, you're using the data to examine your hypotheses in your hypothesis set. So the training set is very contaminated. The test set is completely clean. You don't use the test set at all to make model choices for your model, learning model. But the validation set we think of as in between. It's slightly contaminated. You don't use it again and again and again, but you use it on these finalists, these suboptimal final best hypotheses, in order to pick one. So it's only slightly contaminated. And the walkaway here for this slide is that you want to avoid overly contaminating your validation set. If you need to select more than one parameter for your model, don't use a single validation set. Maybe for one or two it might be fine, but actually carve out a second validation set, which you can do, so that you don't overly contaminate the validation set. Because once you overly contaminate it, the optimistic bias adds up, and your model is going to be wildly off. Okay, so let's take a look at cross-validation. We know that there's this relationship between E out, between your limited final best hypotheses and your full final best hypothesis. If K is very, very small, what happens? Your out-of-sample error is much better because your final best hypothesis in the full data set gets more data. And if K is very small, though, you're going to have a very big difference between your limited final best hypothesis. It's going to be a poor estimate of out-of-sample error. So we want K to be small because we want out-of-sample error on the full data set for G to be very good. We have as much data in D-train as we can so that when we do train, we're going to get good results for our limited final best hypothesis. But when K is small, our validation set is a poor estimate. When K is large, what happens? Well, our validation error is a very good estimate of out-of-sample error, so any model choices we make are going to be well informed. But the problem is that we're robbing D-train so much so that we're going to have really bad limited final best hypotheses G bar. So we have a little bit of a dilemma here. We want K to be small, but on the same token, we want K to be large. So how do we accomplish this? We accomplish this with cross-validation. And so what we do with cross-validation is we try to maximize the number of points we have for training, D-train. And how do we maximize it with a data set of size n? We only reserve one data point for our validation set. So we have n-1 points for training and 1 point for validation. So we're going to construct different data sets, and we're going to use subscript n for a data set, dn, to reference the data set that we obtain when we leave out the nth in-sample point for validation. And so we're going to have n of these data sets. We're going to have script D1, script D2, script D3, up to and including script D big N. And so we have these data sets, and that's how we make the train as large as possible. And so the final hypothesis learned from our limited data set dn of size n minus 1, that's going to be gn minus. And this gn minus is going to range from g1 minus through g big N minus, because each one is going to be trained using d1 up to and including d big N. So our final best hypothesis, because we had the maximum size detrained that we can get, that's going to be a very good, limited final best hypothesis, because it's only missing one data point. But if we look at the validation error, that's just the pointwise error for that gn minus, our only slightly limited final best hypothesis. That's validation error on that held out nth data point, our validation set of size 1. And so that's just a single pointwise error. So that's gn minus on that held out data point. The difference between that hypothesis on that held out data point and the label by the ground truth target function. And so if we take each one of these pointwise validation errors, our cross-validation error, ECV, is just the average across each one of these E1, E2, up to and including E big N, because we have N of these singleton validation sets. And so if we compute that, well, we get this cross-validation error, and it makes the validation set big because we're averaging over n different versions of it, as well as small, i.e. getting a big detrain, because each one is only holding out one data point for validation, and therefore detrain is n minus 1. So we can strike this balance with cross-validation error to make our model choices, and this achieves that balance for making k small as well as making k big. And so you can think of each en as belonging to a validation set. Then it becomes respectable because we're using n points, because this cross-validation is across all of those big N, many point-wise validation sets. Okay, so let's look at an example of cross-validation. So here we have a line on the plane, and we have 3 data points, and we're going to leave out each one of these point-wise validations. So we're going to leave out the first point, E1, leave out the second, leave out the third. Our cross-validation error would just be 1/3, the average of the sum of each one of these point-wise validations. So here, with a linear model up top, the top row, we have a constant model on the bottom row. If we add up these validation errors, we see, okay, well, the constant model is better because I have 1/3 of E1, E2, and E3 are errors. Those differences, that's smaller than 1/3 of this E1, E2, and E3. They're bigger. And so this just says the constant model is better, and we can select the constant model because this cross-validation error is smaller. So this is an example of using cross-validation to do model selection. And in this example, we have the 1-digit versus 5-digit classification problem. And we have average intensity and symmetry as the 2 features that we use to describe these digits. And so here we have the 5 digits, not 1. And here we have the 1 digits that are 1. The 1 digits are blue. And so what we've done here is we have a bunch of features, up to 20 features, transformed using a polynomial expansion of degree 5 of the original feature space. X1, X2 are features, and we have dummy variable X0, which is fixed to 1. And so we have 20 different versions of the features we can use. We can use the first feature, the first and second feature, the first, the second, and the third feature, first, second, third, fourth, etc., up to including the first through the 20th feature. And so we have different feature space representations that we can use for this classification task, and use validation to select the particular model as described by the different number of features that they use, 1 feature through 20 features, as our model selection task. And so we take 500 points at random for training, and we do cross-validation on 500 points. So each of these training sets is going to be 499 for detrain, 499 points for detrain, and 1 point for validation. And we use cross-validation to determine which model to choose, where to stop in terms of the number of features. And we're going to try up to 20 features. And so if we look at this, and this is the graph on the right, we have out-of-sample error in the red, we have cross-validation error in the black, and we have in-sample error, EN, in the blue. So some observations to look at. Here you'll notice that E out and ECV kind of track with one another. It's not precise, but when cross-validation error goes down, E out is also going down. When E out goes up, cross-validation error is going up. When E out makes a big step, cross-validation error also makes a big step. And so that means cross-validation error is a very good estimate for out-of-sample error. If we look at in-sample error, we see in-sample error, as you increase the number of features used, it starts to go down and down and down. But there's a point where E out starts to increase when E in this case, stays the same. So if we run this learning model, we see that it stops at 6 features. Now, if we were to look at the full model without validation, all 20 features, we have in-sample error is perfectly 0, okay? Out-of-sample error is 2.5%. But if we use those 6 features that we get through validation, through cross-validation, in-sample error increases somewhat, but out-of-sample error has a dramatic decrease, and that's with validation. And with validation, the model selected is 6 features. Okay, and you can actually see that in the learning curve. After 6, E out starts to increase, E in stays the same, so we start to overfit at that juncture. All right, so let's look at something that's a little bit more sophisticated than the leaving one out for our singleton validation set size. Now, of course, cross-validation error works perfectly, but the practical problem is, what happens if we have a data set size n equals to, say, 1 million? That means we're going to have n minus 1 detrain is size 999,999. And then DVAL is going to be a size 1. But if we construct all those data sets, script D, we're going to have a script D leaving out the first input, a script D leaving out the second, up to and including a script D leaving out the 1 million data point. So that means when we compute our cross-validation error, ECV, we're going to have 1 over n, where n is a million, sum, and we're going to have that pointwise error, right? Now, of course, if we have n is equal to a million, that means we're going to have to evaluate this a million times, which is a huge computational burden. So we need to strike a balance where we can do validation, but not suffer that computational inefficiency if we have very large data sets. And so one way of doing that is to leave more than one out. And this is this idea of having KFold cross-validation. Now, with KFold cross-validation, a very popular one is K equals tenfold. You take your data set, you chop it up into 10 equal size parts. So you start out and you set aside one of those parts. If it's chopped up into 10, that's 1/10 of your data set. And then the remaining 9/10 of your data set is going to be your training set. And so what you do is you shuffle through, say the first 10th you're going to treat as your validation set, and the remaining 9/10 are going to be your training set. And then your second 10th is going to be held out for your validation, and then your third 10th, and so forth. And so with this, you can strike that balance that you're not going to incur the same issue of having a large number of evaluations of this error for cross-validation, and get a more reasonable computation time and speed up in computing your cross-validation error. And so with your KFold cross-validation, the most popular one people use is tenfold, where K is equal to 10. All right. So with that, that's all I had to say. As usual, please stay healthy, stay safe, and I'll see you all on Thursday.